So good afternoon, everybody. Actually, at the first, I want to return one word: the keynote speaker. Actually, I don't have done that much, and just my presentation, I will say, is a collection of different stuffs. So many of you must know the one food in the Western recipe, the stuffing. So they put together different things, and at the end, sometimes the taste is good, and sometimes maybe not. So hopefully you'll enjoy it. Uh, so I'll go with the topography of Nepal, and the main features are our Himalayas are characterized with rapidly changing topography, and so consequently numerous slope hazards in different engineering structures, and maintaining stable slopes and providing necessary access in road and other structure is very challenging. And our natural slope is more than 70% of the natural slope is between 30 and 60 degree, and our rock wall extends several kilometers up and down, right? So in this context, I think it should not be the special seminar. It should be a normal seminar for us. Okay. Outlines. I try to cover some typical soil slopes and rock slope failures in different parts of the world, and natural slope and cut slope, same thing, and a slope monitoring system, not typical modern, but in contemporary after 2000, and some slope protection measures, general, and I tried to cover very little on the stability analysis and the failure prediction. These are, I think, the new things. Our MSc student might work on this. Okay. The natural rock slope hazards, as my previous presenter already presented, encountered in road and reservoirs, for dams, and river valleys. And similarly, cut slope or built-up slope hazards we encounter in open pit mine slopes. That's not that doesn't exist in Nepal yet, but maybe in recent future, after 10 years or 15 years, it will come. And other one is slope failure during the deep dam foundation excavations. We are designing several mega size hydropower projects with 100 and 200 meter high dams, and sometimes the depth of bedrock is at 100 meter below the riverbed. In that condition, we have to excavate all the way down to the 100 meter, so we'll have the rock slope stability problem on there. And the next one is for surface powerhouse excavation. We already faced it in several projects, and still some are coming. And next, we don't have it because we only have one embankment dam in Nepal. That's Kolekhani. That's 112 meter high dam, rockfill dam, and it not failed. So we haven't done nothing, but it may come in the future. And next is the rail or road embankment failures. One of the evidence for this one is CP Railway, that's Canadian Pacific, because I came from there, so some example of here I use are from Western Canada. It was almost 7 kilometer long embankment, up to 20 meter high, and relatively on the weak foundation, and it fell before they operate the train. So there is a possibility, because we are going to build that train in Therai soon. So I when I start with some natural slope failures, this is the Arun River in eastern Nepal, near the Chinese border. So if you see here, you can see the biggest curve, and this is the river is flowing in that direction. This is the right bank, and this is the left bank. So this is the failure that's this generation of people felt it. and it was 70 years back, and all the mass started to move from here, this point, around 3200 meter elevation, and it went all the way down to the Arun River at 1800 meter elevation, and then made a big heap of the material uneven at the left bank. And same thing was happened here, but we don't know the date. And at that time, 11 people died, and lots of losses of the animals. And the dam started to flow after 3 days, but the dam remained up to almost 20 years. After a small landslide, again blocked the river, and then when it broke, and then it washed the dam after 20 years. So, and this is the photograph that we can see here as the small terrace on the left bank of the Arun River. Similarly, it's also in the Arun River. It's the previous one was a mix of rock and soil slope. So the failure started at 3200 meter elevation, and the failure happened in June. That means before the rainfall. So I think that started with the melting of the snow, because that's almost at that place the snow line is around 2700 meters. So it's started up to 500 meter above. So when the snow started to melt, and it disintegrated some part of the rock, and it started at the top. And when it moved down, it bring all the material on top of the rock. And this one is also in the Arun River. It's exactly in the bend. If you see in the Google map, it's in the bend of the Upper Arun hydropower project, one of the big hydropower projects. And it started not from the top. Mostly, it started from the bottom when the river started to cut the toe of the wall of the rock wall, and there are some feasible joints, and when it breaks the bottom part in tension, then all the material comes through on that feasible joint set. And this is the next one is Jure site. You all know more than me, so I'm not going to describe it. And I'll go to some, these are exactly fell slope. So there are also other slopes which are defined as slow moving slopes. And this one is the left bank of one of the biggest reservoir, that's Revelstock Dam. It's also in BC, Canada. That's 165 meter high concrete dam, and it generates 2400 megawatt. So it's a big one. And this slide is just recently found that it's moving, but in a very slow rate. So less than 1 to or maybe 1 to 2 millimeter per year. And they started to monitor it. Another one is I think it's a very well known. Some of you know. It's Frank slide. It happened in 1903. Several, maybe hundreds people died, and people are working inside this hill. They were coal miners. So when it happened at 4 a.m. I think early morning, and then all the miners were working inside, and they can come out. Some of them are trapped, some of them are rescued several days after. And another big slide, it's also for the reservoir. That's you can see at the bottom here, it's a mica dam that's around 200 meter plus embankment dam, and just upstream within 1 kilometer on the right bank, they found, just after the construction of the dam, they found 2 big slides. And these slides, this one is almost 9 kilometer long and 1.1 to 2 kilometer thick slide. It's moving around 5 to 7 millimeter per year, and it jumps when the pore pressure is high. And we are building some of the dams, so I think these examples are suitable for us. Another one. So those are the natural slopes, and this one I don't have the picture because this picture was taken in 1978. It's also for the same dam, Revelstock Dam, and then when they were excavating a 14-meter diameter diversion tunnel, and they had a failure on just upstream of the diversion tunnel. And you can see, I think, just here, the heave of the around 14 million meter cube of rock, just once. And I think there are very less fatality. Next one we have is from Upper Sanjan. It's a back slope of the powerhouse area. Maybe some of us know. It was in 2016, and the failure occurred after they were excavating the back slope for the powerhouse, and it suddenly collapsed in the morning. And luckily, there was no casualty as well. And next one we all know is the slope of the descender of the Kaligandaki River. And there are some other examples in the failure in the embankment. This is also from the Thompson River Valley. It's in the northwestern BC. You can see the tracks, the railway tracks going here. One is on the upper part, and other one was just on the bottom part. So there are two tracks, and the whole slope collapsed to the bottom tracks. And the last one, I have an example from our very big project, Fast Track. And this is, you can see there are no things. So can you guess what might be the triggering factor here? So it's the toe cutting from the river. So when they were building the road here, and the river swelled in like 100 years flood, and then it eroded the bottom part of the rock and collobium wall. It's not continuously rock, but some part is collobium and some part is rock, and it just cut the bottom, and it triggered the rigs on the top of the road, so it has to be again protected. Another major, I think, cut slope stability issue that comes in the open pit mine. I already said we don't have open pit mine yet, but all the slope stability protections, analyses, softwares, and the equipment, they are developed from the open pit mine experience. These are really huge mines. Some of them are like nearly 1.5 kilometer deep. And the operation of open pit mines is really complex things, because the peoples are working there, and you have to protect the people, you have to evacuate things, and you also has to know when the slope is moving, so when it will fail. And that has to be monitored. And this one is one of the mines in US. So other one is the copper mine in South Africa. We don't have that big mine yet, but hopefully, if we get some more metals, then we can have mines. I think it's 2002. This one is 2002. I don't know the date of the previous one. Yes, in 2002. So I jumped to the slope monitoring. As already said, I just collected things together. So what the instrumentations we use in the monitoring of slopes are inclinometers to measure the deflection, and one new thing, step accelerators. That one I used. It's a three-dimensional array. It comes in 30 centimeter long, 30 centimeter long sensor, and it can measure three-dimensional deformations, X, Y, Z. But it's complex. If the slope is moving really slowly, it's very difficult to determine which direction it's going. But if it is it's moving in single direction, it's very particular, and it's a real-time monitoring. That means you'll get the data in real time. Like in the inclinometer, you go and put the instrument only. Let's say if you measure today and then tomorrow, then you'll get two data, right? But in the case of step accelerator, you can get the data every 10 minutes, every 5 minutes. You can customize the data. Next one is the piezometers that I think we are all familiar with. Piezometers can be piezometer. I have a detailed photograph as well. And next method is LiDAR scanning. It's just like a scanning of the surface today and tomorrow, and they get the difference. The other one is the ground-based radar scanning. It also monitors the slope continuously. We put the radar here, and then show the direction of the slides, and it gets the difference in the distance. I'll show the picture. Another one is we haven't used, but it's in the developed country. They use the satellite monitoring with ground-based reflector at different points. Here is the shell of the inclinometer. So we put it's with from the group. We insert these measuring instruments, and then we get the point, the position of the inclinometer at that particular time. For the shape axle arrays, these are the arrays. They come in 7 meter, 9 meter, and I think even longer if we want, but they are pretty expensive for us. It's like it was $150 per feet, so pretty expensive. But how we can use it? It's on a slide. We can put this arrays like vertically, and then if it is moving in this direction, then you'll get the real-time data. Also here it's showing the concrete putting of the bridge, and you can put together, and it can be placed just in the tunnel like an extensometer, just around the tunnel. Next one is that ground-based radar. It's we put this one in front of this Frank slide. It was in 2010, and when we were putting there, it was -39, the outside temperature. And this one is really heavy. It's more than 250 kilograms, and it needs a crane to lift the things from the ground to the top of this small hut. But how it works is you can see the two lasers here, laser source. So it continuously emit the laser to the slope, and then when it return back, it just record the time, difference time. So let's say if the slope is moved 5 centimeter, then there should be less time for the laser to travel from the source to the slope. That's how it works. Next, we know the piezometers, but piezometers can record there are different type of piezometers. Some record the static data and some can even record the dynamic data. When the train pass or when there is an earthquake, and they can automatically trigger to record the pore pressure. They can be programmed like that. And the most effective things in the pore pressure measurement is, let's say, in the soil slope, when we already know the slope, the shear plane. Then what can we notice in the pore pressure is if there is a shearing or is there acceleration in the movement, we can feel the acceleration in the pore pressure generation. That's how we'll get the information in the piezometers. Okay, so not detailed, but I just summarized some of the slope protection measures. I haven't gone to the stability analysis yet because that's a really big thing and it takes time. So what I suppose, the slope protection measures are based on following factors. The first thing, we can achieve the slope stability from the reduction of the pore pressure, most of the cases, if the slope is not drained and full of water. And the next is the reduction of the slope itself. That means change in the slope geometry. And third one is we can protect the slope bottom from erosion, slope itself, slope surface from erosion. That's how we do, I think, in bioengineering. And the protection from toe cutting, that we put the toe wall. That's why if there is the support at the toe, then it will not move on the top. And next one is slope reinforcement. What I mean with this is either the bioengineering reinforcement or the short bolts that we don't anchor, we just put it there, like in the rock bolting in the tunnel. And next is the slope anchoring. Like if we have a big block, and then we can just put the bolt, In that case, we have to tie that big block in the like a stable rock surface. That's slope anchoring. And another one I will say is the same thing, but it works with the slope anchoring, but we break the kinematic feasibility of the whole rock structure, like the joint and the foliation planes structure. We add something and then we break the feasibility. And another is breaking the moment along the shear plane, that we can introduce, let's say, toe support or even increase the load at the toe. There are different things. So I have some examples. And this one is again the example of the Dutchman Ridge. That's just upstream of the Mica Dam I just described. And this one includes almost 9-kilometer long drainage galleries with at different directions. And then they measure, you can see here the pore pressure before and after the introduction of the drainage gallery. And this pore pressure reduction will certainly increase the friction parameter, I suppose. And that will help the reduction in the rate of the slope movement. Next one is again I'll come to the back slope of the upper Sanjin powerhouse. In the powerhouse, we tried to change the geometry by removing the top unconsolidated soil mass. At the beginning we tried with the bottom toe wall, but at the end when we excavated from the top to bottom and used the reinforcement, the surface reinforcement, it worked, and then there is no need of the bottom toe support. Next one is I just talked about this big rock mass failure at the intake of the Revelstoke Dam, and they introduced here, you can see the two big anchors. They anchor these whole blocks to the stable rock mass, and plus they use these piezometers to continuously monitor the movement. Another one is, we all know the right bank, left bank of the Kaligandaki River, the descended area. There are numerous anchors and the rock walls established, and you can even see the piezometers. But I don't think anybody has checked how the anchors and piezometers are working or not. But it's still the slope is okay. So. So I will come with this one. So this has one particular thing. This again the slope of the Dutchman Ridge. So there was a big question, why it's moving on 6 to 7 millimeter per year but didn't fail. And the most of the people's analysis was because of this toe weight. So if we remove this one and just analyze the slope, then we'll get the factor of safety less than 1. So it is in the road excavation and in the river valley like construction and the dam excavation, it has a big meaning in the consequence. What is the consequence? We don't care. We just cop at the bottom and see the upper slope. And next is it's again the toe at the corner of the Upper Arun project, where the Arun River bend. You can see this one, like it's not the foliation, but it's one joint, and it's just like provide the kinematic feasibility of the whole upper part of the failure. So the bottom part is started not with this, just with the tension fail. At the bottom the rock failed in tension, and when it come to this joint, and it just couldn't support the upper part, and it just moved at, I think, at one point. And next one I will come. This figure is you can guess. The Bagmati River is cutting the toe of the whole slope, and this threaten the upper slope of the recently cut sections. And I don't have any details. Okay, so I'll come to the very briefly into stability analysis because I think it's a really big and important topic, and like I could not cover just now. But for the slope stability analysis, what I suppose is the slope stability methods. The important factors are first the formulation of the failure mechanics. And what we do next is we use the commercial software, but what we use the same commercial software and for the swell slope and for the rock slope. And for the case of I just showed the road section, it has the rock outcrop every 10 meters. And in the middle, there is a colluvium. So where is the failure plane? We put the uniform homogeneous material all the way down and use the software. So you can judge it. You are ours, geotechnical engineers. And for the soil slope, I think if the dominancy is the fine grained soil, most of the slopes are pore pressure driven. So we can manage the drainage efficiently. We can hold them, and we can still use the HM as the homogeneous material, and also the slope geometry and slope material as well. And next thing is the I'll just briefly want to say factor of safety. What is the factor of safety? I think it has the variable meaning. So it's just one means if it is in the existing stable condition, one means the stable condition. But when we analyze and we get, let's say, 1.5, what does that mean? It should be the knowledge-based factor. So how much we know the mechanism and how much we know the material parameters. It should be guided on that. If we don't have the good knowledge on the mechanism and the material parameter, we should have the higher factor of safety. But we know exactly what is that. Then we can even, I think, provide 0.9. Some of our slopes stand even 0.7, right? And next, I will say some of the steps for the modeling of slopes and protection, and hopefully it will work. The first thing is the determination of the slope geometry. We all know that. And then second, and the most important, I'll say, is the identification of the failure mechanism. How the slope is working, how the slope is moving, at what plane, if it is the homogeneous material or the non-homogeneous material, if there is a predefined failure plane or no predefined failure plane, we have to do that. And third is the stress state, including the pore pressure. But we mostly, we have no measurement on the pore pressure, right? In our slopes, we just assume the line. And the fourth will come the selection of the material parameters and the material model. Once you know the top three, then I think that's a straightforward. And next, more important is the introduction of the protection work. And the last one, it should go and back and forth with the introduction of the protection work. We have to check the stability analysis with and without protection work, and that should include the structural as well I think I'll say the hydraulic stability. If it is in the valley. And next one, as I already said, the prediction of slope failure. There are lots of work done actually in the open pit mine field. There are lots of paper, you'll get it, how to predict the failure date. So if you can predict, okay, this slope will fail in the March 3rd, then you will get lots of money. Who will try? Who wanna try? I think our new engineers. Thank you.